The library is called Decimal128. Hello everyone, my name is John and I recently wrote a decimal library for NIM. And my motivation was that I was working on a database driver for MongoDB and realized that my BSON serialization protocol, BSON is binary JSON, supported decimal, but my BSON library did not support decimal. And so I wanted to both make it match the spec that BSON uses, which is a public spec, IEEE 754-2008, but also have it available for any other use in NIM for where people might need a decimal library. Which brings up the question, what is a decimal library? Basically, it's a base 10 numbering system. I mean, NIM supports floating point numbers, and those are fantastic for many, many uses. But if you are in fact taking information from a project that has a lot of decimal math, and you want to make sure that it is very, very accurate and isn't prone to any rounding errors, a decimal can be a solution for that. And I've been asked this question a few times, but not just in NIM, but in other projects as well, about what is the point of a decimal library? Why not just use float? And probably the easiest way to explain why is to actually give you a really quick example of why. So please excuse me, some folks already know this stuff, but we're going to dive into number theory just a little bit. Okay, we're going to look at three numbering systems. First, we're going to start with binary, which is what computers use, of course, off and on, and in this case, 0 and 1. So binary is a base 2 numbering system. We humans typically use decimal, and so we've got digits 0 through 9, so it's a base 10 numbering system. But John, what do the Sumerians use, or the Babylonians from 4,000 years ago? Nobody is asking. Well, they use a base 60 numbering system called sexagesimal, basically 60 digits and I'm not even going to try to pronounce those digits. I mean, I did look them up, but sure enough, there'll be some ancient Sumerian in the audience and they'll get mad. Like, you pronounced it wrong. So I'm not a risk taker. So it's very interesting. They actually counted on their hands using the segments of their fingers because there's 3 large segments in every finger, and they would go through and get up to the number 60 somehow. I'm not a historian, it's just very interesting. But you'll see why I'm bringing up this numbering system in a moment. Let's find out what happens when we try to store numbers in these different numbering systems. Here's a base example that works out pretty well for everything. We've got a fractional number. Use my mouse over here. Fractions, 1 over 2. And in decimal, of course, we know that equals 0.5. In binary, we're going to go ahead and use a fraction point here as if we would normally do that. Now, I'm fully aware that we don't store floating point numbers in a 0.1 format internally, but just for seeing it visually, we'll go ahead and keep it in this format. So 0.1 in binary is a half. And in sexagesimal, it is this thing. And I'm not going to try to pronounce it. But let's take a look at a different fraction. 1 divided by 5. Well, in decimal, that works out 0.2. But in binary, it comes out to 0.00110011001100. It's a repeating number. It is not possible to store 1/5 in binary. And this is the reason why you sometimes, not oftentimes, because they do a lot of tricks with the algorithm in most floating point libraries, where they make it kind of sort of work when you move between decimal and binary. We're going to get into another example of that here in a moment. And of course, in sexagesimal, it works as well. By the way, this odd symbol over here, that's actually 1 digit. It's kind of a morph of other digits. It's kind of like a precursor to the Roman numbering system, which, in fact, the empire was a precursor to numbering. Well, at any rate. Let's take a look at another number, though. This is 1 divided by 3. Now, this is well known in decimal to not be storable either. We cannot store 1 divided by 3 in decimal. It comes out to 0.33333 forever. It is a repeating number. And as it turns out, it's also a repeating number in binary, 0.010101 and so on. But look at this. It comes out even in the sexagesimal. So different numbering systems on a very fundamental level can store different numbers. Now, for those of you who are guessing that this has something to do with the primes of the base, Yes, but I'm not going to get into an hour-long discussion about how that relates to the different numbers. There are, in fact, numbers that don't work with sexagesimal, like 1 divided by 7, another prime, not surprisingly. So when you put in a floating point number into your source code, and say you put it in a literal fashion, you actually say a equals 1.23, the compiler's taking those characters, 1 and a dot symbol and then 2 and a 3, that's actually in decimal that you just typed it in, and it's converting it over into binary internally. And then when you do a $ function against it to print it back out again, it's actually turning it from floating point numbers back to decimal. And that conversion is where you can get problems. An example we'll go into in just in a moment is 99.9 in nim will not store very well at all because of the way the rounding and that fancy algorithm that tries to get past all the conversion problems doesn't work with that particular number. And you'll get 99.90000 and then a 1 at the very end. In fact, let's go ahead and do a quick demo of this. Okay, let's start by simply showing the 99.9 example. Let's run this. Here it is. A equals 99.9 and then all these zeros and 1. It's simply a rounding error as you convert from one numbering system to another. But let's take a look at this example here. Here I'm going to create 99.9 again, but from a different direction. I'm going to first set B equal to 33.3, which I can tell you in advance will print out as 33.3. It'll look just fine. Then I'll multiply it by 3, and let's see what the results get to when we do it that way. Again, we get the 99.9 with all the zeros and the ones from the first example, but B equals 33.3, printed just fine. But now it underflowed just ever so slightly to 99.8999 repeating. Again, lots of numbers that can't be stored in different numbering systems. And here's the key. Let's go ahead and get into where and when you should use this library. Because I'm not trying to make this a selling point as being the solution for all your floating point math. In fact, far from that. If there's not a good reason to use the slow, awkward library that I just wrote, don't use it. This is really meant for conditions in where it's really critical to get the numbers right. For example, if you're working on a financial system, you don't want your bank statement to be off a little bit. Or worse, the sum total of a large number of statements or transactions to be off in an accumulative manner. As you keep adding more and more in there, it gets off a little bit more and more and more. That's going to cause all kinds of problems, including making it near impossible to audit your projects. This is also used for scientific projects where you do want to keep track of not only the decimal numbers that you're being input into the system, but you also want to keep track of significance, which I'll get into here in just a little bit. But where you don't want to use this is where you really need the numbering system to be fast, because this is not fast. It uses up a lot of memory, and frankly, this is only useful if you're really getting data in a decimal form in the first place. For example, if you're writing say a game, you're writing it in Godot, and you're pulling in say a 3D graphics asset of some kind, and it's coming in as binary floating point math in the first place. Well, you're inputting it in binary. You're manipulating it in binary in your graphics drivers, and then you're outputting it to the screen through another graphics driver, again in floating point math. Turning it into decimal will actually make things worse. If it comes in binary and goes out in binary, keep it in binary. It's only when you're getting numbers in decimal and out in decimal, and its accuracy is really, really critical, that you would really fall back to using something like a decimal library. Just a tiny bit of details, and I'm going to show you some quick examples. The decimal library does store things internally as a fairly large object. 37 bytes of memory are used for each individual number, at least. The 128-bit part of the library is about the serialization. So if you're using this with a BSON document coming from MongoDB, or if you're using it from some external source that has a standardized storage format, going to the IEEE format makes a lot of sense, and the procedures for doing that are in the library. But to speed up the processing of the numbers internally, it's kept in a much larger format that makes it easier to manipulate the math. It does do rounding in order to maintain the proper precision. And it uses an algorithm which I won't go into here, but it's called Banker's rounding to even. One of its benefits is that it has a statistical effect when you're doing a large number of numbers that have to be rounded, that they'll even out to about 0. We'll have little overall effect on your operations. It is not an algorithm I came up with, but it is really commonly used in financial institutions, and I think it's actually a pretty good algorithm as a whole. All right, well, let's start by simply reproducing the problem scenario we had in the beginning, 99.9. Let's store it. Notice that we're passing in the number as a string. You can pass it in as a floating point number or as an integer, but then you get back to some of the same problems. Actually, not so much with integers, but you'll get into problems with putting it as a floating point number because then you've already done the decimal to floating point conversion before it's turned back into decimal. See what I'm talking about? So keep it as a string. And in fact, in general, if you're storing this on a database or an external system that doesn't support decimal numbers, it only supports floating point numbers, then I recommend that you store the numbers as a string. Here we go, 99.9. Now let's show you a little bit about scaling. So let's make another number here. Let b equal, okay, here we've got a number that actually has more zeros after the decimal point. And by the way, significance only has to do with numbers on the right. Numbers on the left are significant to infinity. And again, I'm not going to get into number theory about why that is, but that number is the same thing as this number. And it's, if you think about it, that kind of makes intuitive sense too, but it's actually also number theory behind it. It really only changes the behavior of your math from the right-hand side of the numbers. Or if you want to be technical, you call it the least significant numbers. And there we go. When we print out this, it actually shows all of those extra zeros. And let me show you where this gets useful in math. Here I've made the numbers a little bit different. We've got 99 point, and I put all nines in the end, but we've got significance going out 7 points here. And we also have 10.00, which shows 2 scale precision points after the decimal point. We'll print those both out, but then we're also going to add them together and see what kind of number we get back. And here's where significance gets to be important. You can't create significance from nowhere. If a number is 10.00 and we don't know any more after that, adding more digits afterwards doesn't make sense, because when you add something to unknown, it doesn't make something known. You know, 4 plus unknown does not equal some other number. It means unknown still. Let's go ahead and run this and you'll see. And there we go. We got 99 point, all the nines, 10.00, but when we add the two numbers together, we get 2 digits after the decimal point because we're maintaining the proper scale or precision of the number. And let's show this in an opposite direction as well. Let's take something like the population of Italy. For the year 2020, the population of Italy is estimated to be about 60 million people. However, writing it down like this, 60 million, oh, by the way, you can put underscores in the numbers and the new decimal library handles that just fine. You don't want to write it down like this because 60 million is not correct, actually, because it's an estimate. There's not exactly 60 million people, not one more, not one less. It's somewhat around 60 million. In fact, it's only accurate really to, well, let's for the sake of this example, let's say it's only accurate to 2 digits. You know, it might be more than 60 million. It might be a little bit less than 60 million, but we're going to say it's 60 million-ish. Well, the best way to write this is, in fact, to put it in scientific notation. And we do that because we want to restrict the number, the levels. We do this because we want to restrict the amount of precision or significance to the digit. So it's 60 and then unknown numbers afterwards. So the way we would write that is in scientific notation, 6E6. Let's go ahead and run this and see what it looks like when we print it out. Oops, spell it right. There it is. In fact, it converts a little bit to a more proper scientific notation here to 6.0 E plus 7, but it's the same thing. But now let's see what effect this has. Because if you think about it, if I add another million people, you know, 1 E6, that will actually change the number. But let's say I do something silly like let more people equal . add 25 more people. Well, if you think about it, that won't change the number any. Not because it didn't actually change the number of people in Italy. It does. It's because 60 million was an estimate. We don't know the exact number of people in Italy. So adding 25 means you still don't know the exact number of people in Italy. So let's add those numbers and see what we get. All right, here's our new code. 25 more people, adding the numbers together. Let's see what the total population is now. As you can see here, we added 25 more people and the total population still reports 6.0 E plus 7. It didn't change because it's honoring the proper scale and precision of the original numbers. Okay, we'll go ahead and stop here because I could talk for hours about numbering systems, even though I'm not a mathematician. At least I didn't plan on being one. At any rate, let's go ahead and close this up. The library is, in fact, only partially done. I got it done enough for my purposes, and I got it to working in very basic functions. I can do serialization into and out of the library. I can do storage and conversion and most of the support functions you'd ever want out of the thing. And it does addition and subtraction. But what it doesn't do multiplication or division or powers or exponentation or anything like that. And so if you are interested in getting involved with this project, we do need help fleshing this library out fully. Hope you all found this interesting. Thanks for watching.